Uh, First of all, thank you, Alessandro, for giving this talk. So this week, quantum fields matter than string seminar, we will host Alessandro Tomasiello, and he will be talking about new punctures for six-dimensional conformal field theory compactifications. So Alessandro, whenever you're ready, you can start.
Thank you. Thank you so much for inviting me to this nice new seminar series. I think it is a good idea for such online talks to continue. The topic for today is perhaps counter-cyclical. It is not perhaps a very fashionable topic, but it is dear to me, and so I have been wanting to do something like this for a long time, and I may have been able to make some progress together with this fine collaborators of mine, Fabio Puzzi, Nopadol Meccaria, and Brandon Robinson. There is some work that has already been published on a slightly different topic, which I will also mention. But the most important part is some work in progress that we are hoping to finish in a few weeks. By the way, you see my pointer, right? I don't remember how these things work. Okay, good. As you all know, quantum field theories are harder to define in higher dimensions. So a classic example is that even if you consider the usual, well, I'm writing here F mu, but more generally make it Yang-Mills, well, this becomes relevant in the UV. So it becomes relevant as an operator. So the G Yang-Mills explodes in the UV, which means that well, we don't know how to even define such a theory. And for some time, I think people weren't even sure whether quantum field theories would be well defined at all in higher dimensions. The string theory gives helps because it helps give evidence for the existence of non-trivial conformal field theories. And of course, you can view conformal field theories as some kind of building blocks for the definition, for the study of quantum field theories. They are the fixed points, low energies or also high energies. So this is a good place to start when to study quantum field theory. There is perhaps the most famous one defined by, or whose existence is strongly suggested by string theory, is this CFT that lives on the stack of on a stack of n and fibranes, which has this extended supersymmetry. But there are many more which have this reduced supersymmetry to a minimal 1,0. And they live on more complicated Boyne systems, as we will see later. One point that perhaps I should make about this, this problem of defining quantum field theory, so perhaps you're not that interested in higher dimensions. Well, I like to say that it is analogous to the problem of defining gravity in dimensions 4 and higher, because it's actually the same issue. So the Ricci tensor, so the usual Einstein-Hilbert action basically suffers from the same issue here. For the same reason, this operator is relevant in dimension bigger than 2. So here we get that Yang-Mills is ill-defined in dimension bigger than 4 this time. So, well, perhaps we can, there may even be some analogies between the two issues. But so in general, what can we do with these theories? Well, we don't know them. We don't have all the relevant data from string theory. In general, we believe them to be non-Lagrangian. Well, non-Lagrangian, of course, means that we don't know Lagrangian. No, I'm not sure if it means that it doesn't exist. But for now, at least, what we can say, what we can do is this: we believe that there is these theories have modular spaces of vacua, and once you pick a vacuum, you can flow to the infrared, and well, not flow completely to the infrared, but at some intermediate scale, you have an effective field theory that you can describe that is partially with the Lagrangian. When I say partially, so I have this pseudo action here. What does it mean? Well, in general, there are also some issues with self-dual fields, where writing the action, which make the writing the action a bit contentious. But this is not really the core of the issue. The core of the issue is not this self-duality here. After all, some equations of motion can be written. The more difficult part is really writing the interactions for the original theory. And for those, we really have no idea at the moment. Compactifying, so what do we care? Well, maybe you don't care about 6 dimensions. We don't live in 6 dimensions. But if you put such a theory on a Riemann surface, then you do get a CFT in 4 dimensions. Well, so if you put a CFT, say, on a Riemann surface cross R4, as you go to large distances, the Riemann surface is going to look tiny. And so effectively, you will see theory in that lives in 4 dimensions. This is not always a CFT, but sometimes it is. Also, we will see some examples. And anyway, even if it isn't, sometimes it is a CFT together with some stuff that is decoupled or that can be ignored, some bosons, for example. A famous example that has been discussed at length is this n=2,0 theory that I mentioned in the previous slide, and this leads to the class S theories. I'm sorry, many of you might know this story in detail, but let me review it for the benefit of anyone who might not know this story. So the CFT4 is obtained by assembling simpler models. What do I mean? Well, you can start by considering the compactification on a particular Riemann surface, which is non-compact. It is a sphere to which 3 points are, from which 3 points are cut out. And we call these punctures. The associated theory, well, we don't know much about it. We do know much about it, but we don't have a Lagrangian. But it has been called in various ways, but that is popular is the Trinion theory. And it is believed to have 3 factors of UN flavosymmetry associated to the 3 punctures. And then you can go ahead and glue these. What does this mean? So if you glue 2 Riemann surfaces, 2 spheres with 3 punctures, you can create a non-trivial Riemann surface. If my hands are represent the 2 spheres with missing points, you can glue them like this, and you obtain something that has, of course, genus 2. And so this is a procedure to create a non-trivial Riemann surface, but correspondingly, the gauge theory, so the field theory that you obtain in 4 dimensions is obtained by gauging the diagonal of the UN flavosymmetries that we had previously. So you do that in the case that we are considering now. We are gauging this diagonal formerly flavosymmetry with an n=2 multiplet. This is the rule. If you do that, you obtain the theory associated to this genus 2 Riemann surface. This is the basic idea. You can, here's another example. You can also glue in such a way as to not get rid of all the punctures, but for example, only identify. You can also identify glue together two punctures on the same sphere, and that produces this theory here, which is topologically associated to a torus with a single puncture. And this theory, in this case, this theory is in fact Lagrangian, and it is called n equal 2 star. It is the theory obtained if you write n equal 4 in n equal 2 multiplets and you give a mass to the hypermultiplet. Okay, so there is a general story here due to well, it has its roots in work by Witten, but it was formulated in the way we know it today by Guy Orton, and many people worked on it. So a word about the punctures, because this is going to be important. The total, you can start with the full flavor symmetry, but then you can actually Higgs it. So there are various ways to Higgs it, and they leave invariant a subgroup of the original Higgs or the original flavor symmetry. The rule is this one. So in particular, so here there is a jump. You just look at the jumps of, so there's an associated Young diagram to the way of Higgsing, and you look at the jump from each row to the next, and each of those gives you an SU number of jumps. So here an SU2 and SU1, which is nothing, and here an SU2, and here nothing, because SU1 identity. So there's a full hierarchy of such Higgsings. This structure appears also for other theories in many contexts, but it is particularly important here. In some situations, you even have a Lagrangian realization for, if you have not just this puncture that you're Higgsing, but also others, sometimes you can assemble them so that at least a piece of the theory can be realized with the Lagrangian. And these Lagrangians are associated to diagrams called quivers, and sometimes people call them quiver tails. So this procedure here sometimes can be described at least partially with the Lagrangian. A measure of the CFT degrees of freedom of this of the resulting for the theory is the so-called A anomaly. In general, there are many anomalies that you can consider, but if you consider the Weil anomaly, which it is a CFT, it is exactly a conformal invariant, except if you put it on a curved background, it will no longer be so. There will be a violation of the conformal invariance, and we can compute such a violation. And it can be written in general as a sum of two, well, in 4 dimensions, it's a sum of two particular quantities that are written in terms of curvature. One is the so-called Euler density. It is the guy that, when integrated, gives the Euler characteristic of 4-dimensional space. And its coefficient is called A. Just for reference here, so if you compute it with on a vector field, on a spino, on a Majorana spino, on a scalar, it gives you some order 1 numbers that are tabulated somewhere that were found many years ago. Why do I mention? Well, because now we can get a sense for what this theory is, how many fields it has, even though it is so it is just an approximate notion, because after all, the theory is not supposed to have a Lagrangian, the CFT. Well, we can measure at least approximately what its number of fields. with this anomaly. It has been computed with various tricks, and the result is the following. It has a contribution that is proportional to the characteristic, the Euler characteristic, indeed the integral of this guy. And its coefficient is actually proportional to the, approximately proportional to the analogous quantity, analogous Weyl anomaly coefficient of the Weyl anomaly for the theory in 6 dimensions. And additionally, it has some contributions associated to the punctures. This guy is a function of which Young diagram you have. You will have a certain expression, which if you for this Young diagram here, the original one that we had. So you have to think that this is the, when I was drawing the punctures in the previous slide, I was starting with this one with the full SUN Flavor symmetry. And then in that case, okay, just for reference, in that case, the function would be order n cubed. But as you go down this hierarchy of Higgsings, it will get smaller and smaller, corresponding to the fact that you're Higgsing the theory, so you're losing more and more degrees of freedom. Okay, so this is a mini review of the compactifications of this 2,060 theory. In this talk, we are going to, the remainder of this talk, we are going to wonder if this picture can be at least partially extended to 1,0 theories. As I will review, there are many 1,0 theories. Actually, I will not review this. I will review a subset, notable subset of 1,0 theories. You will see why I'm focusing on those. The full story is much bigger, the full story of 1,0 theories. But the question, the underlying question is how much of this story, this class S, so-called class S story for compactifications with 2,0 theories can be extended to 1,0, to lower supersymmetry. Of course, the resulting theories, as one should expect, the resulting theories in 4 dimensions will only have n equal 1 supersymmetry.
So can I ask a question?
Absolutely.
Please,
by the way, please interrupt me at any time.
In the previous transparency, what was the n? I mean, there are too many n's, and the previous
the n, sorry, the
for...
n in the previous transparency, the n was so here it was n equal, it was 4, just because I didn't want to, because otherwise there would be many Young diagrams. So you always start with this completely horizontal Young diagram, and then you have all the Young diagrams with the n boxes.
So this is the number of flavors.
This is the number of flavors. Yes.
Yeah. And in the next, I mean, in this second half, this is also the number of flavors. Okay.
Yes. In particular, the
n equals 1, this is 0, right? It should be.
A good question. For 1, it gets 0, which I suppose is, it is, yeah, for the 1-dimensional case, it's not even in guy. Yeah.
Thank you.
So the interesting part is where you put many together.
Yeah.
But then there's another thing which is which might even be better to notice. I should have done so. The mystery of the 6-dimensional theories is that typically their numbers of degrees of freedom, the number of their degrees of freedom goes like n cubed. Unlike what we are used to in 4 dimensions, where you can build. So typically, if you write a Lagrangian, you will end up with an n square number of degrees of freedom, because you start with the Young-Mills. It is believed that somehow this 6D CFT has managed to find a way to, I don't know, with fields that have tensorial structure with 3 legs instead of 2. But it is hard to make this more concrete. There are many ways to compute these numbers, and they all seem to agree, but it is hard to find a Lagrangian that realizes this expectation.
Thank you.
Okay, any further questions on this lengthy introduction?
Can I also ask a question?
Yeah.
So you mentioned that if we compactify an n equals 1, 0 theory, we will get an n equals 1 theory in 4 dimensions. Can we obtain an n equals 2 theory by compactifying? Because in the case of n equals 2, 0 compactifications, we can obtain n equals 4 diagonals.
Yes, you can compactify no torus.
And then can we get n equals 2 by compactifying n equals 1
Yeah,
on
yeah,
6
yeah. So you
dimensions?
can do that. You can do that, and this has also been studied, but it is not straightforward to obtain. There are proposals by, in fact, I think I have an extra slide, but perhaps I don't think I included it, but maybe at the end I will show it.
Okay.
There is a proposal by Omori, Shimizu, Tachikawa, Yonekura for what happens if you compactify, for what kind of theory you get when you compactify on some of these 1,0 theories on a torus. I don't want to show I don't want to show this proposal now because I haven't. There are many 1,0 theories, and I only have the slide for one type of. But there is also some work on that. Yes, that is. You might also argue that this might be the place to start, but it turns out that it is not much easier than what I'm going to do today. Maybe surprisingly.
So if you're going to talk about n equals 2, I can ask a question later about that.
No,
or I can ask it now.
Wait, please ask it now.
Okay, so in n equals 2, we can demonstrate confinement by mass deformation, right? Via the Seiberg-Witten procedure. So how can we understand this confinement in the 6-dimensional perspective?
Oh, if there is a counterpart of that computation, and well, I mean, so for you have in mind all the Seiberg-Witten computations. In a sense, some of the story. So for this n equal 2 theories that I was talking about, a lot of what I have shown you comes actually from the knowledge, detailed knowledge of the Seiberg-Witten curves. So those, in a way, the Seiberg-Witten curves of those theories are related to those Riemann surfaces. So in a sense, the Seiberg-Witten computation kind of goes through. It becomes similar. Some of that can be repeated.
Okay. Thanks.
Okay. Let me now tell you what the plan is. I want to show you some 60 theories. As I said, not all. Those that are holographic, namely that have an ADS dual in string theory. Or actually, I should say, those have a known ADS dual. And those happen to be in string theory. Then I'll talk about what we can say about the compactifications without punctures. And these two parts will be about old stuff. And finally, this is a strange title for what will be the final part of the talk. So disclaimer, I have to, there's a lot I try to summarize a lot of stuff with many pictures. So sometimes it will perhaps look like there aren't many details, but please ask and I'll try to provide further details. The same story applies to the Gaiotto story. That's also not just visual. I mean, there is more, there are actual computations, but in order to summarize the story, pictures are useful. So suppose you want to provide that 60 theory. What can we do? So here's some simple strategy that people have tried to carry out. So you can start with the gauge multiplet, but a couple to matter. I told you that gauge multiplet by itself had some issues. So let me try to see if I can improve the situation with this. So there is a certain choice here. If you take an NF equal to NC, that well, can be is supersymmetric and is not anomalous, at least. Okay, that's a good place to start. Moreover, there is something that can be written. Like I mentioned this, we don't know the action really, but and even writing at least we can write a pseudo action, something that is almost an action. So from it you can get almost all the equations for motion, but you have to supplement it with the, some self-duality constraint. It is not perfect, but it is something at least. And even so, it is surprisingly difficult to write such a pseudo action that is supersymmetric, but it has been done. The interesting feature here is the following. Instead of having the usual trace of f square, it has the trace f square is multiplied by a scalar. The scalar comes from this matter here. So this is a visual representation. So the gauge multiplet is here. This tells us what the flavor group is, and this link represents somehow all this matter, hyper multiplet and tensor multiplet. Tensor multiplet in 6 dimensions in particular contains a scalar, and this is the scalar that I'm talking about here. Due to the coupling, the way you need to couple these things together, it turns out that you have to introduce this term. So the gauge coupling has become dynamical. This is the lesson. And you, in particular, you may ask, so in general, if you set phi equal anything, the theory is not renormalizable. I said that a few slides ago. But it is curious to think about what happens for phi equals 0 at the origin of this tensor moduli space. I call the tensor moduli space the one that is parameterized by the scalar in the tensor multiplet. Well, because when this is 0, if you think about it, normally this is 1 over g mu squared. So when phi is 0, basically you're going at a strong coupling point. And you may speculate that there's some interesting dynamics here, hidden here. And already you may wonder, maybe there's some CFT hidden here. Well, based on this field theory alone, perhaps it will remain a speculation. But we can go further, and I want to convince you that indeed there is a CFT there. But first of all, let me generalize this. How? Well, first, I have separated the flavors into 2 groups. Now, let me gauge this one. So it was a flavor symmetry. I can gauge it with a second gauge group. And now it becomes a little chain like that. This is an example of what people call a quiver. Well, really, a quiver is something more complicated when there are also arrows. And indeed, a quiver in a common language is a set of arrows. But if you in this setting, if you can keep going and now gauge this guy and the next and the next, and you will get a chain, maybe not a quiver, but a chain of gauge groups. And notice that at each node, this equality is satisfied, and this turns out to guarantee once again that the anomalies are in this theory are cancelled. This is constraint actually still doesn't isolate, doesn't identify, is not satisfied only by this particular chain. Here is another possibility. If you make this linearly growing, it turns out that it will satisfy this because, for example, this gauge group has, which has 2 colors, has 1 plus 3 flavors. So constraint is satisfied. The next, okay, 3 colors, 2 plus 4 flavors. okay, the constraint is satisfied, and so on. But at this point, I can also generalize it further. Here is something crazy. It looks crazy, perhaps. It grows. It turns out that you can realize many possibilities when the ranks, the gauge theory ranks, grow. And they grow. So when they grow with a certain slope, well, you don't need anything else to satisfy that an f equal to nc constraint. But sometimes when the slope changes, such as here, you can introduce some further flavors. So for example, here, this, satisfies it because 8 plus 10 is 2 plus times 9. And this wouldn't satisfy it because 9 plus 10 is only 19, but then you can add the further one. So it turns out that if you think about it, any convex piecewise linear function that is convex will satisfy these constraints. So you get a list of possibilities. So these are effective field theories for now. But the crucial point, since this is, after all, I said that at some point string theory was going to come into the game. The crucial point is that now all this class that I've been talking about can be engineered, people say, realized on a system of branes. The gauge groups are live on D branes that are on top of each other. It is well known that such branes give rise to gauge groups. These dots here are NS5 branes, and it turns out that they so it is very well known in other dimensions. Perhaps you might have heard it in other dimensions that when an S5 brane separates two sets of branes, it gives rise to matter fields. And in this dimension, this is not just a hypermultiplet, but also a tensor multiplet, exactly the type of matter that I was talking about for a link 2 slides ago. And this comes about basically because of the strings that go from one segment to the other. The strings have to jump over, so to speak, these NS5s, and this is what gives rise to this type of hypermultiplet. Okay, I don't have the ambition of explaining all this diagram. Suffice it to say that so you can all this general class of supersymmetric effective field theories can be obtained on this brane system. But now, what is the CFT point? Well, okay, sorry. The scalars, first I need to ask what the scalars are that appear in the action. Remember that there were scalars in the tensor multiplets. Well, they are related to the positions of these NS5s in this direction. So previously we had that phi equals 0 was a promising point. Well, now it looks like a promising point might be to put them all together. Indeed, I said even at the beginning for the theory living on M5 branes that it was the interesting part was the interaction between all the branes. So if I put all the NS5s on top of each other, it will create some interesting interaction. Well, in order to put them on top of each other, I need to, so I have done one step. I have in this diagram, I have repeated the same thing, but where I have moved only one NS5 towards the other. Or if you want, I have moved this other brane, this D8 brane. And one important point is that this will modify the diagram. There is a creation of a new brane. This is something that might be familiar in the new context to people who study things that are fashionable now, such as generalized symmetries. And the reason that this happens here is basically the same. only at the time we didn't call it generalized symmetry. And well, if you keep going, you can finally put them all together here. Instead of putting 17 dots on top of each other, I have made a big dot. And now all the other branes create a structure like that. I have done all the computations for you in order to make a sensible diagram. And the one thing to notice is that you don't need to do this every time. Actually, the combinatorics of all these diagrams can be summarized very elegantly with a couple of Young diagrams, which is morally related to the Young diagrams we had a few slides ago. Okay. Now, the thing that leads us to believe that this is a CFT point is exactly the fact that we have put a lot of branes on top of each other. Before, it was just the fact that it was strongly coupled. Now we see that even in the string theory engineering, all the branes are on top of each other. So even though we don't have really a Lagrangian, we believe this to be an interacting quantum field theory. Why would it be a CFT? Well, there is a way to see it, which is that the corresponding solution, if I go very near this object, this brane intersection, will create an ADS geometry. This is famously what happens near the D3 branes. Many D3 branes engineer an equal 4 superior mills. In this case, it is more complicated to see that it gives rise to an ADS geometry, but I have done it long ago. First, we classified all the possible ADS solutions. And then we saw that there was a correspondence with these theories that I was talking about. So this is let's say an important piece of evidence that these things are indeed CFTs. Here I don't present computations. I just give you a couple of pictures to hopefully convince you that the general picture holds together. First of all, I don't have the brane the supergravity solution associated to this brane intersection, but I do have the near horizon limit. And it is actually a very simple gravity solution. It looks like this. This is the internal metric, sorry. Oh, sorry. No, it would be the full metric if I hadn't forgotten to write here the ADS7. Here, I should write ADS7 plus this is the internal metric. And the alpha, what is alpha? Alpha is a function of a single coordinate z. So this is a cartoon where the coordinate z runs horizontally, and the function alpha is a piecewise cubic function. Its double derivative is a piecewise linear function, and because of various string theory reasons, it needs to satisfy certain integrality constraints. And when you look at those integrality constraints, you get a convex function that such that when you restrict z to an integer, this should be an integer. You stare at it long enough, and you see that it's exactly the same data that were present in the class of field theories that I have that we have considered in the previous slide. Moreover, if you now try to compute the A anomaly for these theories, which can be done, this is now the 6-dimensional A anomaly. It precisely matches with what you can compute with this metric, with this ADS7 cross internal space metric using holographic methods. Well, I shouldn't say precisely. This computation can only be done in the so-called holographic limit when there are when the analog, so basically the number of gauge groups that we have here becomes large. this is the number of an S5 brane, so it's directly similar to, it is very similar to the number of M5s, the N that we had a few slides ago that Özgür asked me about
So,
previously.
can I ask a question? This
Absolutely.
Z, alpha is a function of Z only.
Sorry?
Alpha is just a function of Z, and Z is the dimension of the D8, right?
This dimension here, so this in this cartoon, sorry, perhaps my explanation was only partial. In this cartoon, this direction here is meant to be a two-sphere.
Yeah.
The
Okay.
two-sphere grows as a function
It's
of that,
horizontal.
and then it goes down. And so it is topologically a three-sphere now.
Yeah. Okay. Okay. Thank you.
Thank you. So, yeah, of course, I cannot draw this very convincingly, and this is just a cartoon.
Yeah, sure.
But, you know, so for, and another thing, so what are these creases? Why do I write this discontinuities of the derivative? Now, well, I mean, the thing is continuous but non-differentiable. Why? Well, this correspond precisely, the location correspond, and numbers and locations correspond precisely to the presence of the 8 branes in this diagram. So you see the D8 has become here a D8 brane in the solution, and the back reaction of a D8 brane will make it precisely give rise to such a non-differentiability.
Okay. Thank you.
It's a kind of singularity, but a very mild one. Okay, so this is an old story. And it just covers what we can say about 6 dimensions. So we are slowly going towards where we need to go. Let's go a little faster then towards where we need to go. This part will be actually, I don't want to say much because, well, CFT without punches, CFT4 without punches. Basically, remember this story. If you compactify on a Riemann surface, you expect to find a QFT in 4 dimensions. So, well, what is I have used previously in this slide, I have used holography to convince you, hopefully, that these things are CFTs. How can I convince you now that when you compactify them to 4 dimensions, you still get a CFT? Well, there's a holographic method also, which is that if you should find a solution related to this one by replacing the ADS7 with an ADS5 cross a Riemann surface, precisely this Riemann surface here. In fact, you would want to have a full, so in successful cases, we have the full interpolating solution that realizes basically this RG flow. It is in one limit, this gravity solution looks like this, and in the other limit, in another limit of the, if you follow the radial, what would be the radial coordinate of ADS, well, you will find a limit like this. So if you can find a solution like this, then it is supposed to be the dual, the holographic dual to this RG flow. And so it tells you, oh, okay, you can indeed compactify and get a CFT in 4 dimensions because ADS5 signals a CFT4. And this actually we found also many years ago, directly after the ADS7. In fact, it helped us making the ADS7 solutions analytical. Previously, they were only known numerically. This is now only the, just for illustration, you see I write here that this is distorted, and indeed it is distorted in a very precise fashion. The little numbers that appear in the solution have been changed. This 2 changes to 3/2. But you can find for each ADS7 cross M3 solution, you can find the corresponding one with ADS5 cross the Riemann surface. There are also similar stories if you want to compactify to lower dimensions. In this fashion, you can presumably obtain 3-dimensional CFTs, 2-dimensional CFTs.
Can I ask a question about the previous
Absolutely.
slide?
Yes.
So you had some twisted sphere in the M bar tree, and some like D5 became D5 plus A. Is that a U1 gauge field?
I have some twisted spheres. Did you this twisting?
Yeah, in the previous slide.
This twisting here. You mean?
Yeah, yeah, exactly. So is that a U1
It's
gauge
necessary.
field?
Good question. Okay, so morally, yes. However, remember that I don't really know this is part of the frustration. I don't really know the Lagrangians for any of these, but it does seem to suggest that you basically this is part of where this comes from. Yes. So if you study how you can compactify a CFT, you will see that to compactify it on a Riemann surface, you usually need such a U1 gauge field. Now, in the Lagrangian, it is hard with the Lagrangian, it is hard to answer because I don't really have a Lagrange.
Yes. Okay. So it's expected to be a U1 gauge field, but it's not
It is
really
like, yeah.
established.
Yeah. So yeah, it is a compactification that is twisted, if you want, more precisely. Yeah. Yeah, there's heuristic reasons that indicate this. Now, punctures. Finally, you get to the new stuff. So all the story that the old story suggested that we could compactify also not just the class the n equal 2,0 6D CFT, but also all the others that I mentioned, the 1,0 theories that I mentioned on a Riemann surface and get the CFT4. And so at this point, a natural question is, can we build the same story as Gaiotto did for the 2,0 theory? Well, I hope I convinced you that a crucial part of the story was the ability to fuse to glue together some building blocks. And we had the trinions for the 2,0 theory. Presumably we'll have some other trinion also here, and we will be able to glue them, and we'll be able to Higgs the punctures, all that story. Can we do that for this modular 1,0 theories? Well, so okay, sorry for the silliness. At one point it was suggested that by one of our postdocs, Paul Richmond, that if we manage to do that, perhaps since these are in massive 2A, the theory that the version of string theory that where we found these solutions was massive 2A, well, massive 2A trinions, or perhaps minions for short. Okay, forgive me. The idea now, then you would, well, I didn't want to draw two minions, poor minions, when you glue them together, that looks gory, but the idea is that you would do the same as Gaiotto was doing. Now, to find this, to find out about this, the progress we made was based on thinking of these punctures as defects. This is not a completely new idea, but there has been some progress in the understanding of defects, and this is what the final part of this talk. But what are defects in a quantum field theory? Of course, the defects abound. I mean, they can be boundaries, or there can be impurities where I don't know, they can think of the Kondo effect. There's some extraneous defect in the C of CFT of QFT that you understand better. In a CFT, the formula that I showed you earlier for the Weyl anomaly get modified by contributions coming from the defect. And in fact, there's so there's a general characterization for what happens in the bulk for the Weyl anomaly, meaning people have classified all the possibilities, all the possible things that can appear. If you want, you can use the Vesdomino consistency conditions, all these old-fashioned techniques to understand what is the general structure here. With the defect, the number of possible things that can be written here explodes. In fact, so depending on the dimension, there can be 20 terms here, but there is one that is the more important that seems to play a special role, which is the one that multiplies the Euler characteristic of the defect. Now, I have used holography to characterize to to show that the CFTs exist, and now I want to use holography to understand these defects as well. So here, this cylinder here is traditional representation of anti-de Sitter in global coordinates. And okay, this is time. And so here I have tried to, perhaps without much success, I have tried to draw a defect on the boundary. And the holographic realization of such a defect is something that goes inside. And typically you compute interesting quantities about such as this anomaly of this object by considering an object, typically a brain, that goes inside ADS and ends on the assigned defect. The CFT, of course, lives on the boundary. The defect also lives on the boundary, but its holographic dual is something that a brain that goes inside. And there are various techniques to compute this anomaly coefficient here from the on-shell action of the brain. Okay, first, the stuff that we already published last year. We found it easier to consider codimension 4 defects. These are not the punctures that we want for the story, but it's a bit of a parenthesis. But I think it's easier to understand. So let us start from here. Basically, here we want to consider, so this defect is a string defect that is a bit like an instanton relative to one of the gauge fields. From the point of view of the effective field theory, this is its description. It is realized in the brain diagrams that we saw a few slides ago by putting yet another brain. So remember that this segment here consists of many brains on top of each other. They realize one of these gauge multiplets. In this case, there are 8 on top of each other, so they become this SU8. And here you insert this brain. Well, it will become a string defect for this guy. Of course, I mean, to see this clearly, you need to, instead of this drawing, it is better if you have a table which says what brain is extended along what direction, and if you do so, you kind of see where the string lies. If you now redo this brain rearrangement that brings you to the CFT point, remember from a few slides ago, it turns out that this D4 becomes a more complicated object that also has some D2 brains. What this means in the gravity dual is that the corresponding the brain that you should consider in the ADS dual is not actually a D4, but a bound state of D4 and a D2. In fact, something I didn't say is that I was calling these objects here D8 brains. That's kind of a lie. It would be better to call them D8, D6 bound states as well. And it turns out that the position in this Z direction, remember that this horizontal direction is called the Z, is related to how many D2, what this D2 charge is. When it is 0, for example, this D4 wants to collapse all the way here, and it becomes a single D2. There is some zoology like that. But in principle, there is a clear correspondence with where you put this D4 and where you put this bound state in the ADS realization. Now, funny story. In fact, we did the beginning of this, I think, in 2017. But then for a long time, embarrassingly, we couldn't actually do a computation that related to anything in field theory. We couldn't compare the predictions that we got to anything in field theory. Finally, we managed to do it, but there is a trick. We don't have the gravity solution where also this D4, D2 is back-reacted. We treat it as a probe, namely we use the open string realization where we use the brain action not the and we ignore its how it deforms the previously given ADS7 solution. So there are still some computations to do, but it is a lot less challenging than finding the full solution. And the computation, so here's the brain action. This is the this square root is because I'm considering the Dirac-Bonifeld action. But magically, or there are several simplifications, and in the end, you get something very simple. The result is proportional to the value of the function alpha that we saw, but evaluated at the position here, z equals j, where j is the D2 charge of this object. A very simple result. And the part that was difficult was to match it to something in field theory. In the end, we managed to do it. I mean, there is a challenge as always because these are not Lagrangian theories, but some computation can be done reliably in the effective field theory. And it turns out that this can be reinterpreted in the field theory like this. This is because if you look at the Cartan of SUN, it looks a bit like a discrete second derivative, and it's the ranks here are related. The ranks of the field theory, if you remember from a few slides ago, are related to the double derivative of alpha. So this is a bit like taking the second twice an integral of twice a derivative, and this is why you get this match. Okay, I'm concerned that this equality here I didn't really explain as it deserved. So if you're curious, please ask me. Perhaps later. Now let's get to the final point, as I have probably only 5 minutes, right?
I mean, I
Could I mention?
No.
What was the answer? Yes or no? You have 0 minutes.
You can go ahead.
No, you can continue.
So now we get to the unpublished part, the codimension 2 defects. I have, so in the previous slide, I had this diagram for the codimension 4 defects, and then I also had the table. Well, now I have given up giving a diagram. It becomes complicated, in my opinion, and it is not very informative anymore. Keep in mind that it is the same diagram that engineers the CFT 6 that we know and love by now, but we studied what type of extra objects we could add to the story, no longer so that they give rise no longer to string defects, but to 4-dimensional defects. And in the brain diagram, if you follow the rules that tell you how to combine brains together so that they preserve supersymmetry, we identified these 2 possibilities. What do they correspond? Can we see them also in this ADS diagram? Well, we performed in separate analysis for what brains are BPS in the ADS7 solutions. This is not terribly complicated. You find that though perhaps it took us longer than we should have, of course, but for the D4 brains, it is quite straightforward. If you can, so this will be a D4 brain, so okay, 5 dimensions, and you make it extend along an ADS5 inside the ADS7. Remember, this will end on a defect at the boundary of the ADS7. And internally, then only a point is left. It turns out that this point needs to be at the where the alpha is maximum, which basically corresponds to the middle of this solution, some midpoint on this cartoon. But what about this other possibility, the D6s? Well, these are more interesting because actually the D6s are always D6, D4 bound state. This is what turns out. And they have more complicated shape, but interestingly, that shape has a very simple expression. It is always a constant divided by cos theta, where theta is one of the coordinates on the S2. Remember, this is topologically, the cartoon looks like it's topologically a two-sphere. Really, it is should be thought of as topologically a three-sphere, and this is this S1 here that you see is topologically an S2 in the actual solution. But if you think of, so if you call theta this direction here, well, you get a non-trivial shape on the as the internal realization of this defect. It's as if the D4 was puffing up and getting bigger and bigger. It's a bit like a Myers effect. Actually, the same could be said about the D6, D4, the D4, D2 bound states that we saw in the 2 slides ago. So a more complicated computation can be carried out also. So these are condimension 2 defects in the ADS7 solution. But there's one further complication. We don't really want just to have a codimension 2 defects in ADS7. We want to have punctures in an ADS5 cross sigma solution. So these are should be defects with a different asymptotics. They shouldn't go far from the defect. You shouldn't retrieve ADS7. You should retrieve ADS5 cross sigma across a Riemann surface. Well, you can repeat, fortunately, the correspondence between the ADS7 solution and the ADS5 cross sigma solution is so nice that the results are kind of the same. And the next step, you can compute. I told you that there is a procedure to compute the contribution from the defect to the A anomaly from the action of the branes. Well, the results in the ADS7 solution and the ADS5 cross sigma solution are very similar. They just differ by factors of 27 over 32, which is a number that some of you might have encountered if you have played with superconformal field theories in 4 dimensions. So and this is the universal result that we get. We get this quantity for the contribution of the defect to the Weyl anomaly. Recall that we have this formula. Now, if you want for dA, you can just the idea is that you integrate this over the Riemann surface, and you will get finally a formula for the A anomaly. You will have this A6D times 2G minus 2 plus contributions of the defects, exactly like in the class S story that I told you many slides ago. Only now, this is no longer that precisely that polynomial and n-cubed that I gave you. Will be more complicated with that because the theory, the 6D theory, is more general and more complicated. And these will be basically what I gave you in the previous slide. It was an integral alpha. Well, in practice, I don't know, we can evaluate it if you want to see an example. If we go back to the, basically I can go back to, if I set this flux to 0, this is gives us almost back to the, not quite to the class S, but to n equal 1 analog of the class S story. And then I can, here, I can give you a concrete number. And this matches what people had computed in class S. And again, you see here the 27 over 32. There's even a paper called 27, which has 27 over 32 in the as a title by Tachikawa and Wecht. Okay, I'm done. Are you disappointed? Perhaps I am. Well, because what have I done here? I have only computed the contribution to, so I have given a formula basically for the for this 4D theory, But I can only find this formula reliable when these things are not too large. Otherwise, I don't know if this formula is really reliable. And moreover, I haven't done all the other things. I haven't done all the gluing. Well, hopefully this is the first step. So let me conclude. There are many 6D theories. There is almost a classification. Well, I haven't told you about the classification, but believe me, there's almost a classification coming from string theory. And in particular, within this classification, there is a nice set that we have for which we know the holographic dual. They give rise to, upon compactification on a Riemann surface, to many, many more 4D theories. But we would like to understand these 4D theories. And we would like to do something similar to what was done in class S, namely to be able to decompose these 4D theories into these minions and glue them together. At least today we found semi-reliably in a certain regime the contribution to the of these punctures to this for the anomaly. And moreover, we now know at least what characterizes this anomaly, these punctures. What are the possible punctures for these theories? Before we didn't even know that. Remember, for class S, we know that they are characterized by a Young diagram. And now I'm giving you, basically, I'm giving you some alternative set of data for this for the theories. This might be a small step, but okay, it is a first step towards hopefully establishing a massive two-way analog of class S. Thank you.
Thank you, Alessandro, for this beautiful talk. If there is any question,
you didn't stop me. I went over time.
Is there anyone who wants to ask questions before stopping recording?
Actually, I have a question. So you mentioned the four-dimensional A coefficient related to the six-dimensional A coefficient. I remember people like Cordova and Dumitrescu doing some constructions on the A theorem for 6 dimensions. Can we use their constructions to understand the A theorem in 4 dimensions? Like, can we precisely establish this result?
So, as you know, in 4 dimensions, we have a proof of the A theorem.
You mean the
Komarkovsky
Zohar,
and
Schwimmer. Okay.
So
yeah,
4 talks ago, there was Komarkovsky here, so he was But conversely, in 6D, it is problematic.
I see. So I'm asking the question in the wrong order.
So in 6D, well, I mean, you can get some insights, but as follows. In 6D, one would like to have a clean proof. The analog of the Komarkovsky-Schwimmer argument was attempted by Elvan, Friedman, I forget, and doesn't seem to work straightforwardly. But if you believe that there's a classification of 6D theories, you can just brute force go and see it. Now, the papers that you mentioned offer some more sophisticated understanding into why, how one should get there, and why A theorem might work. And indeed, I mean, you get some reasonable insight by comparing the two. So, yeah, the link is there, but exactly the opposite direction.
I also wanted to...
In this case, it is more that you learn about 6D from the 4D.
Okay. I asked the question wrong. I also wanted to ask you, like, so you're viewing these punctures as defects and get some insights into the anomaly contribution and so on. If we consider a duality defect, like in supersymmetric issues, we have a lot of dualities and we can construct duality defects with them. If we consider these defects, what do we gain by studying them?
Duality defects such as S-duality, like an S-duality wall or stuff like that.
Which have some non-invertible fusion algebra. And then how can we realize that in the string theory perspective?
So that's a very good question. Yeah, so I haven't tried to do that. You're only the second person to ask me this. So I have done more. There is already rich story that you can do in supergravity to look at S duality defects, to look at S walls that arise in 4D supermills that you can study holographically. And it is a beautiful story. It would be nice to repeat it here, indeed. I think here we need some analog. The difference is that in 4D, we have a theory that realizes an S wall. It is very clear what here it is. It is the TSUN, they call it. Sorry, all this TSUN or
yeah, I heard about TSUN.
It's not, some people call the trinium TN. I'm not talking, it's not the same theory at all. This TSUN realizes an S duality wall within an equal 4 supermills. And I have been told by Sarah Pasquetti, for example, that there is an analog in higher dimensions, and that would be presumably the start of this story. But yeah, there's that's something that one could do. Yeah.
Okay. Thanks for the great question, by the way. Great talk, by the way.
No, great question also. Great question. By the way, there are no wrong questions. There are only wrong answers.
Are there any questions before we start recording?
Can I ask one question? It's a naive question if anyone doesn't have a question. Okay, you know, we had the tables for codimension 2, codimension 4 defects and their combination with branes. What is this table determined by? I mean, is it only determined by supersymmetry, or are there anything else?
This table here, I mean, for example.
Yeah.
Yeah, exactly. So very good. Sorry. What something that I keep saying defects. While I was giving the talk, I realized that this is incomplete. I should have said BPS defects, because these are the ones that so we in this game we are often obsessed with BPS, the BPS condition, right or wrong. I mean, this is the ones that we can control, where we such that if we can compute something holographically, we can trust that in the field theory, which is a priori a different regime, the two will match. So here I explicitly looked exactly for the defects that are BPS. There is a simple rule. I mean, this rule is not does not capture the full reality of what how branes can be BPS with one another, but it is a rule of thumb that takes you far. You need to remember, you probably know this, the number of directions that are transverse to a brane and parallel to another needs to be a multiple of 4. And you can see here between, I don't know, this D8 and this defect D4, 1, 2, 3, 4. And so on. You can keep going and you will find. So this is how I have determined this table. Like I said, this does not exhaust. So these are the simplest ones. And indeed, I didn't quite rely on this table. So this gives you an indication. When you go in a ADS solution, it is easier. I mean, it is easier to directly do an analysis in the ADS solution. And then there are methods that are more sophisticated than the one I just described. And this is how, if you just relied on the rule of thumb, you wouldn't see that there are bound states, for example. So these two guys can somehow fuse with one another. How do you fuse these two objects? It may not be evident, but it can be done. You need to have the brane of lower dimensionality and on the one of higher dimensionality like this. But I don't know. So I'm in this finger realizes this this direction here, and this hand realizes these three directions here, and this is what you do. And now the bound state is when they create a funnel, they do like this, and somehow the idea is that this will once you go to the ADS solution, it will have something to do with this shape here. We cannot control all these steps. This is just an idea. The beginning and the end of the story are solid. All my drawings with the hands are not.
May I ask a question?
Please.
It might look a bit off topic, but I'm currently working on the low dimensional holography and lower than 3 at least, and I'm currently working on DF theory. So when I was studying on it, I come across this particle-on group quantum mechanics holography, and I tried to work on it. And at least when I took SL2 DF theory, and it simply finds a quantum mechanics, particle-on group quantum mechanics on the half plane when we go to the boundary of the half plane. And also I tried it for wedge space, and on wedge space, since we have the wedge, we have some kind of a line defect. And that defect, if included, it gives Schwarzschild quantum mechanics on some like. So I tried to find its symmetric extension for at least n equals 1. And I now want to add some punctures to the half plane so that maybe it will affect the what we found as quantum mechanical theory on the line of the boundary of the half plane or the wedge. So, but I don't know any framework that I can add that puncture so that puncture somehow relies on that Lagrangian formalism so that we can find through the geometric holographic coordinates or the other things so that we can find the contribution of the puncture. So do you have any suggestions? So where should I look and how can I add
do you have a brane realization for all this, or do you?
No, at least not to my knowledge. I don't. But maybe we can just have those punctures somehow, but I really don't know how. But I believe that it will be really interesting to have how the F theory on the bulk will affect the quantum mechanics that we find through those punctures, at least, and how it changed. For example, when I study on it, I found that the F theory with OSP 1,2 will correspond n equals 1b supermultiplet. It's really useful for at least for the black hole physics, and Strominger did a lot of work on it. So maybe with the punctures, there will be some different geometries that we can find and different holographies that we can find. So do you have any suggestion on how can what roadmap I should take at least?
Yeah, so introducing punctures is a bit of an art. I mean, in the big, so in this talk, I have been guided by the brane realization. On the other hand, so one might say, oh, so this motivated my first answer, go look for brane realization. However, Gaiotto was guided rather, well, also by brane realizations, but also by the Seiberg-Witten curves and by taking suitable limits of the Seiberg-Witten curves. Although in your setup, I cannot imagine an analog of this. Yeah, you caught me a bit off guard. I cannot think I now have a good strategy. Finding defects is a bit of an art. I mean, even finding boundaries that can be, for example, that preserve supersymmetry, that even are stable in quantum field theory. In general, it's not that simple. I mean, the other things that people do is, I mean, if you're forgetting about all this string theory mumbo jumbo, is consider to define punctures is to consider poles, loci where the fields acquire have certain boundary conditions, certain strange behaviors, such as a pole for a field, or you declare that a certain field must go to zero there, stuff like that. It's I mean, yeah, then this is not answering, right?
No. It was really helpful. Thank you.
No, I'm not sure. I don't think it was. I have an idea. Please write me an email, and I'll try to think about it some more.
Yes,
Could
happily.
you do that? I mean, I cannot guarantee.
Yes.
I cannot
Yeah,
guarantee I'll get a better idea, but off the top of my head, I'm only telling you generalities.
Yeah, thank you. I will happily write you a mail and talk to you about it. Thank you.
Thank you. Please do. I'm not. I'm not.
I will.
No,
I will.
I'm not kidding. I'm not joking.
Thank you. Thank you for your answer.
Thank you, Alessandro.
Two people spoke at the same time.
Yeah,
But
Özgür Hocam.
I was just saying thank you.
Thank you. Nice to see you.
If there's no question, we will stop recording. Then I will.
I have a question. Can you hear me?
Yes.
Okay. So, do we get some additional info about the theory if you look at the monodromy between these punctures?
Like if you turn one up
Exactly. Exactly.
Good question. Yeah, in this case, I don't think so, because they don't have anything that is attached to them. But that is a situation for these ones you don't. But that is yet another situation that you might consider. I haven't tried. It might be that I have seen other situations where we do. In this case, I don't see it, but maybe there are some generalizations of these objects. In other words, I kind of declared that I wanted a single object with nothing attached. It is more often the case that you can gain information by, and perhaps I didn't focus enough on this, by studying what happens if you, even if you put two punctures close to one another. In fact, if you have followed this story, I mean, this was the key insight by Gaiotto, that such limits of different duality frames that then, if you do it in two different ways, suggest dualities between different theories.
Yeah, I see. Thank you.
Thank
you. Any other questions? Okay.